force is a push or a pull. A force of some kind is always required to change the state of motion of an object. The combination of all forces acting on an object is called the net force. The net force on an object changes its motion. The net force depends on the magnitudes and directions of the applied forces. When two forces are in the same direction, their magnitudes are added and the direction of the net force is in the same direction of the two forces. When the forces are in opposite directions, the two magnitudes are subtracted and the net force is in the direction of the larger of the two forces. If the two forces are opposite in direction and equal in magnitude, the net force is zero. When the girl holds a rock with as much force upward as gravity pulls downward, the net force on the rock is zero. A stretched spring is under a stretching force called tension. The upward tension in the string has the same magnitude as the weight of the bag, so the net force on the bag is zero. The bag of sugar is attracted to Earth with a gravitational force of 2 pounds, or 9 newtons. There are two forces acting on the bag of sugar, the tension force acting upward and the weight acting downward. The two forces on the bag are equal and opposite. The net force on the bag is zero, so it remains at rest. Mechanical equilibrium is a state where no change in motion occurs. Whenever the net force on an object is zero, the object is in mechanical equilibrium. This is known as the equilibrium rule. The sigma symbol stands for the sum of. The capital F stands for forces. For a suspended object at rest, the forces acting upward on the object must be balanced by other forces acting downward. The vector sum equals zero. The sum of the upward vectors equals the sum of the downward vectors. The sum of the forces equals zero, and the scaffold is in equilibrium. What forces act on a book lying at rest on a table? One is the force due to gravity, the weight of the book. There must be another force acting on it to produce a net force of zero, an upward force opposite to the force of gravity. The upward force that balances the weight of an object on a surface is called the support force. A support force is often called the normal force. The table pushes up on the book with as much force as the downward weight of the book. The two forces add mathematically to zero. The state of rest is only one form of equilibrium. An object moving at constant speed in a straight line path is also in a state of equilibrium. Once in motion, if there's no net force to change the state of motion, it's in equilibrium. An object under the influence of only one force can't ever be in equilibrium. Only when there's no force at all, or when two or more forces combine to zero, can an object be in equilibrium. When the push on the desk is the same as the force of friction between the desk and the floor, the net force is zero and the desk slides at a constant speed. If the desk moves steadily at a constant speed, without change in its motion, it's in equilibrium. In this case, the sum of the forces equals zero means that the force of friction is equal in magnitude and opposite in direction to the pushing force. The tension in the rope is 300 newtons, equal to Nellie's weight. The tension in each rope is now 150 newtons, half of Nellie's weight. In each case, the sum of the forces is equal to zero. To find the resultant of non-parallel vectors, we use the parallelogram rule. Consider two vectors at right angles to each other. The constructed parallelogram in this special case is a rectangle. The diagonal is the resultant R. When Nellie is suspended from rest from the two non-vertical ropes, is the rope tension greater or less than the tension in the two vertical ropes? You need to use the parallelogram rule to determine the tension. Notice how the tension vectors form a parallelogram in which the resultant R is vertical. Nellie's weight is shown by the downward vertical vector. An equal and opposite vector is needed for equilibrium, shown by the dashed vector. Notice that the dashed vector is the diagonal of the parallelogram defined by the dotted lines. Using the parallelogram rule, we find that the tension in each rope is more than half her weight. As the angle between the ropes increases, tension increases so that the resultant remains at 300 newtons upward, which is required to support Nellie's 300 newton weight. When the ropes supporting Nellie are at different angles to the vertical, The tensions in the two ropes are unequal. By the parallelogram rule, we see that the right rope bears most of the load and has the greater tension. You can safely hang from a clothesline hanging vertically, but you'll break the clothesline if it's strung horizontally. Copernicus announced the idea of a moving Earth in the 16th century. One of the arguments against a moving Earth was this. Consider a bird sitting at rest at the top of a tall tree. The bird sees a worm, drops down vertically, and catches it. It was argued that this wouldn't be possible if Earth moved as Copernicus suggested. The fact that birds do catch worms from high tree branches seemed to be clear evidence that the Earth must be at rest. You can refute this argument using the idea of inertia. Earth moves at 300 kilometers per second, but so do the tree, the worm below, and even the air in between. Objects on Earth move with the Earth as the Earth moves around the Sun. Earth doesn't need to be at rest for the bird to catch the worm. If we flip a coin in a high-speed car, bus, or plane, we can catch the vertically moving coin as we would if the vehicle were at rest. We see evidence for the law of inertia when the horizontal motion of the coin before, during, and after the catch is the same. The vertical force of gravity affects only the vertical motion of the coin. Flip a coin in an airplane, and it behaves as if the plane were at rest. The coin keeps up with you. That's inertia in action.